All right, man. Let's see if we can wrap up the rest of this review. So this is going to be the calculator parts. There are a couple questions that don't have a calculator, but that's fine. Let's see if I can get through the calculator part. I don't have a way of showing you the calculator, so maybe next time. But I will definitely work the problem out and show you what you need to type into the calculator, and then I'll give you the answers. And you're gonna need an Inspire for sure for this part. All right. So compound interest. So let's just start with the compound interest formula. So it's some future amount. It's equal to some initial amount. 1 plus the rate divided by the number of times it's compounded. And the exponent is going to be the number of times compounded times t. Some time, typically years. All right, so number one, investment. How much would you have to invest? So I'm going to stop right there. That right there is implying that we don't know how much we're investing. Right? How much would you have to invest? So what do you need to start with? I.e. P. We don't know what P is. To have in the future 30K. Right? So this is going to be our future amount, right? 3 stacks. So then after 8 years, so this is our T. In an account earning 7.25%. So a percent does me no good in the formula. But we can always turn a percent into a usable decimal by moving the decimal places 2 places to the left. So 0.725. And it's compounded monthly. All right, again, that's n equals 12 because there's 12 months in a year. So we have all the pieces of our puzzle. So let's plug it all together. All right, so we got 3 stacks. So 30 grand is equal to some amount that we're looking for, right? Times 1 plus the rate. So 0.0725 over 12 because it's compounded monthly. And this is raised to 12 times the number of years, 8. Okay, so at the end of the day, right, this piece right here, this is just a number, right? Who knows what this number is, but it's a number, and it's being multiplied times P. So to solve for P, I'm going to have to divide by whatever this number is. So what I'm saying is that you're going to divide by all of that. Both sides. I'm being lazy not writing in the parentheses because you get the picture. But the calculator part, what you're going to put in the calculator is this part on the right. Right, 30 grand divided by all that thing on the right. So that's what goes in the calculator. So when I put it in just like that, it comes out to, I'll go 2 decimal places since we're talking money. All right, 16,826.29. If you want to take it to the nearest dollar, it'd be $26. So I think knowing that the 30K is the A value, not the P value, that's That's pretty important, I think. All right. Number 2, you deposit 4,500 in an account. Okay, so what value is that, A or P? It's P, right? It's the amount you're starting with. That earns, so this is our P, 2.5%. Again, I don't care about 2.5%, but I care about 0.25 because we want to move it 2 places to the left, to the left, to the left. Find the balance after 3 years. So T is equal to 3. And it's compounded depending on A, B, or C. All right. Monthly, N is going to be 12. Quarterly, N is going to be 4. Continuously, we'll talk about that in a minute. All right. So the future amount, 4,500, 1 plus 0.025 over 12 raised to 12 times 3. Now, this is going straight into the calculator. There's no dividing by nothing. We just put this in the calculator and see what we get. So 4,500 parentheses 1 plus control division 0.025 over 12 raised to 12 times 3. So you would have, at the end of the 3 years, $4,850.10. That's compounded monthly. All right, compounded quarterly, I'm going to utilize the calculator and make this work for me, right? I'm just going to up, enter. Treat it like a video game, right? Up, enter. And then I'm going to change all the 12s to 4s. So the 12 that's in the bottom, and then the 12 that's in the exponent, I'm changing those to 4s because it's compounded quarterly. When I hit enter, so I guess it's what's showing you what I did. So 4,500, 1 plus 0.025 over 4, that was a change. 4, that was another change, times 3. So all I did was up, enter, and change the 12s to 4s. And then I'm going to get 48, 49.35. So it's not quite as much. Some change. Okay. All right, same problem, but continuously. All right, so notice this word here, continuously, implies a completely different formula. It's the future amount equals the initial amount times E, which is a constant, RT, APERT. Okay, so filling in what we know is going to be 4,500 times, right, that's our p-value, E, which is a function in the calculator. The rate is the exponent, 0.025 times t, which is 3. So this is specifically continuously. When it says continuously, this is what you got to use. Like, don't try to use something else because it ain't gonna work. All right. So this is what I put in the calculator. Now, remember, E is not E that is in the keyboard. There's a function, E, that's 2 buttons left of 1. It says e to the x. So 4,500 e to the x. It automatically populates the exponent. So I'm going to put 0.025 times 3. When I hit enter, we get all right, 48.50, 48. So compounded continuously is slightly better than monthly and quarterly. Just if we were wondering. All right. Hopefully that matches the key. All right, number 3. So the model y equals 15 e to the 0.05 t. So this formula indicates the number of toothpaste caps y that a new employee can screw onto the toothpaste tube per day after t days of being on job. All right, so what's this saying? This saying that this formula, okay, so you got some dude that works in the toothpaste factory. So so the number of days after he's been there, t, then this will give you the number of caps that he has screwed on to the toothpaste tube in a day, per day. Okay. All right, so how many toothpaste caps have been screwed on? So we're looking for a Y by employee on the first day. All right, so first day, so this is day 1. So T equals 1. So in the calculator, we're going to do, so Y is equal 15 E.05 times 1. So it comes out to 15,609, blah, blah, blah. All right, so I think it's worth saying that typically you would round a number up if the decimal is more than 5. But you can't screw on half of a cap. And no matter how hard you try, 15.7 is not 16. It's either 15 or 16. There's no in between. So if I had to say, I'd say 15 caps. Do working slow. So 15 caps. All right, how many toothpaste caps have been screwed on by an employee after 13 days on the job? All right, so 13 days. So same problem, up, up, enter. And I'm changing 1 to 13. Okay, this number is going to be 28.733, blah, blah, blah. All right, again, I think it's safe to say that he's up to 28 caps a day. Okay. C, how many days of employment are required? So how many days, right? So now we're looking for T. So T is the unknown. We want it to produce 100. So how many days would he have to work there until he's like showing out, right? Doing 100 a day. So this is going to be 15 E.05 to the T. All right, come next week, we're going to know exactly how to solve this problem, like precisely, because the variable is in the exponent. Right now, we don't know. So your options are pretty simple. Since we're looking for days, days are whole numbers. 1 day, 2 day, 3 day, 4 days, so on. So you can just start hand jamming numbers until you get close to 100 or the closest to 100. I wouldn't worry about the point, whatever. That's a way. Another way is that you can use the Inspire and graph the right side as a function, then graph the left side as a function, and then see where they intersect. All right, so after some trial and error, it's about 38 days. All right. All right, so here's the first little no calculator for section. All right, so we want to simplify. So just combining like terms. All right, so we're three things being multiplied. So all the coefficients times each other. So 3, right? Because 3 is the coefficient. And then because we have common bases being multiplied, we add the exponents. So e to the x plus 3x plus 4 plus 2, right? All the exponents are being added. So it's going to be 3 e. All right, so 3x plus x is 4x. 4 plus 2 is 6. And can't combine it anymore. All right, number 5. What do you think? So, a couple different ways to think about this. It's being multiplied. So, one way is to turn the square root into an exponent or to break it up. It truly doesn't matter. So, I'll let you decide which way you like best. But what I'm saying is the square root of 8 times the square root of e to the 4x. Or you can break this up. Square root of 8, that can be simplified. 2 times 4. So I can bring out a pair of 2. So this is going to be 2 root 2. 2 root 2. All right. This e business. So it is a square root. But if I turn it into an exponent, right? Like if you say, okay, well, where'd the square root symbol go? Turn into an exponent. 1/2 exponent, right? Because this is the root, right? It's implied that there's a 2 here. You never see it because we don't ever write it. Now we can apply the exponent rules. When you have a power raised to a power, you multiply. So 4 times 1/2. 4 times 1/2. So e, 4 times 1/2 is 2x. So I think that's the simplified version. I don't think it gets any simpler than that. All right, number 6. Same idea, right? As before. You could split this up. You could simplify first. You could split up and then simplify. So the way I'm gonna do it is let's handle the inside first. There's 27 and 3. That's gonna make a 9, right? Because 3 goes into 27 9 times. So this is really a 9. And it's being multiplied by 4. So really what we got is 36. Because 9 times 4 is 36. We have e's in the top, e's in the bottom. So when you have common bases and you're dividing, it's always top minus bottom. So e to the 7 minus -5, which just means plus, right? Minus negative means plus. So 7 minus 5. Now notice there is no more e in the bottom, right? There's no e in the bottom. It's moved up to the denominator. Same thing is going to happen with the x. X to the -2, top minus bottom, so -6. All right, now when we start simplifying this thing, we're going to get the square root of 36. E, 7 plus 5, 12. And then x, -2 minus 6 is -8. Okay. Just like the last problem, we can split this up. Square root of 36 times Square root of all this other stuff. All right, first off, square root of 36 is 6. That's nice. I'm going to rewrite. So e to the 12, x to the negative 8 to the 1/2 power, right? That's what it means to be a square root as an exponent. All right, I'm going to apply exponent power rule, I guess you could say, by multiplying. So this is going to be 6 e to the 12 times 1/2, which is e to the 6, and then x to the negative 4. All right, in the last step, we don't like negative exponents. So 6 e to the 6 over x to the 4 is now positive, right? It moved down to the denominator and became positive. We don't like negative exponents. So the idea is that we cleared the fraction as best as we could, even though we ended up with a fraction. That's cool. You simplify the coefficients, and then you combine all the common bases. So you don't want multiple e's or multiple x's, right? You only want one of each variable as best as possible. And that's what it is right there. Okay. I want to make another video for this. No, let's keep it pushing. All right. So part 3. I'll probably make a timestamp for this. All right. In an exponential growth model, the model you see here, right? This is simple interest, right? Not compound interest, just basic interest. We want to identify the initial amount. So the initial amount is going to be 527. The growth factor, that's the part that has the exponent, right? So 1.39, that's the growth factor, right? The whole part inside of the parentheses. And then the percent increase. So it's increasing because it's bigger than 1. How much bigger than 1? That's the question. 39%. Right? 0.39. It's 0.39 bigger, but we turn 0.39 into a percent by moving the decimal place 2 to the right. Right? When you have a percent and you want to make that into a decimal, you move it to the left. When you have just a decimal and you want to make it to a percent, you got to move it to the right. So 39%. Right? Everything is in relation to 1. How much more than 1? How much less than 1? So if it's exactly 1, no matter what power you put on 1, the answer is just 1, and 1 times 527 would just be 527, and there's no growth or decrease. You understand what I'm saying? So it has to be bigger than 1 or smaller than 1 for it to grow or decrease. That's the point. Okay. That was it. That was all we needed. All right. So hopefully you get that. Growth factor is everything that's in the parentheses. And the increase or decrease, that's going to be how much more it is than 1 or how much less it is than 1. All right, so let's do like a quick little example. If this was 0.39, this is 0.39. Obviously, it would be a decrease because it's smaller than 1. But the point is, that the question would ask, decrease, how much is the percent decreasing? It ain't 39%. It's going to be, right, if it was at 1 and it subtracted some amount to get to 0.39, like what is the amount? That's what it's asking. Like how much under 1 is 0.39? It'd be like 0.61. Or is that true? 6, 7, 8, 9 plus 10. Yeah. So 0.61. So the percent would be 61% if it was 0.39 is the growth factor. 0.39 if it was the growth factor, 61% would be the decrease, right? Because that's how much 61% is how much it's less than 1. All right. Number 2. In 1996, there were this many computer viruses and other computer security incidents. So this is some current amount. So P. During the next 7 years, so T, the number of incidents increased. So it went up, meaning bigger than 1, right? Increased by 92% each year. So 0.92. Write an exponential growth model giving the number N of incidents T years after 96. Okay, so it's going to be N, right? That's the number of incidences. 2573, because we have to have some starting amount. Because that's that in 1996, they took account and said, okay, this is how much it is in 96. Then as the years go on, it's going to increase. So 1.92 times the number of years. So here's the model. All right. About how many incidences were there in 2003? What's up, 03? All right. So this is going to be 4, 5, 6, 7. 7 years. 7 years after 96. Right? 4, 5, 6, 7. So T is equal to 7. That's what that means. Right? This means T equals 7. So this is going to be straight into the calculator, just T is 7. 2573, parentheses 1.92, right arrow, caret 7. Caret's the exponent symbol, by the way. All right, so N, when T is 7, N is 24748.71823. So you can't have 0.71823 of a virus, right? So we can either call this 4 or 5, right? Like, I think you're doing a disservice by rounding it up. I really think it's just 4, right? Okay. When were there this many computer security? Okay, so now this is your N value. And we want to figure out how many years it took to get this. All right, so 125 equals 2573, 1.92 T. All right, so you can start just hand jamming numbers in for T, or you can either graph this right side and graph the left side and see where they intersect. It's not a lot more, actually. It's actually less than 7. Oh, I put the comma in the wrong spot. Ooh, it's slightly less than 6. Slightly less than 6 years. Right, but more than 5. Way more than 5. So if we wanted to get like a decimal on this, and you could figure out like, 5 years and some months. But how long did it take? 6 years. Less than 6. Not including 6. Okay. Number 3. The number E of eggs and leghorn chicken produces per year can be modeled by this equation. All right. Where T is the age in years of the chicken. So, however old the chicken is, it will produce a certain number of eggs. All right, identify the initial amount. So, initial amount, that's 179.2. The decay factor, switch up the colors. So, the decay factor, it's the part inside. Okay, so the percent decrease, here we go. This is how much less is it than 1? Right? The percent is not 89%. I don't care what they say. It's actually 11%. So try to justify to yourself, where the heck did this dude get 11 from? That's how much it's less than 1. Right? So 1 minus 11 is 89. That's where 11 comes from. So the percent decrease is 11%. All right. Estimate the egg production of a chicken that is 2.5 years old. So this is the T. So to the calculator, 179.2.89 to the 2.5 power. So the egg production, it's 1.339. I mean, that's really close. That's really close to 134, but 0.9 of an egg is not a whole egg. So I'm going to predict 133. Or estimate, rather. We're estimating. All right. All right, here's another no calculator part. Whoopee. All right. So tell whether the function represents growth or decay. Oh, too easy. And give the percent increase or decrease. Let's go. So check it out. This is going to be, so remember, do we have it over here? No. All right. So it's always going to look like this, right? Some initial amount, your growth or decay factor, and then the year. Right, this guy right here, that's the growth or decay. So 1/5 represents the growth or decay factor. So is it growth or is it decay? Well, you got to compare it to 1, bro. Is it less than 1 or is it more than 1? This thing is less than 1. So this is definitely decay. But not only is it decay, we need to say, okay, well, how much, what percent is the decrease? So I need a percent. So 0.5, 1/5 is 0.2. If you don't know, if you don't know, now you know. It's 0.2, right? Because think about it. 2, 4, 6, 8, 10, right? There's 5. So each fifth is 0.2. So how many 0.2s is this less than is this less than 1, right? It's going to be 0.8, 80%. It's an 80% decrease, right? Because, again, 1/5 is equal to 0.2. We say, okay, compared to 1, how much did I had to decrease from 1 to get to 0.2? And you had to decrease by 0.8, right? You started at 1, and then you started decreasing down, and you got to 0.2. Well, how far did you go? You went 0.8. So 80%. 80%. Okay. Number 5. So the factor, it's the number that is attached to the variable. And you always compare it. Okay, so this is growth or decay. You compare it to 1. Is 3 bigger than 1? Yes. So this is growth. Growth. All right, so how much bigger than 1? Well, it's 2 whole numbers bigger than 1, right? So from 1 to 2 would be 100%. And then from 2 to 3 would be another 100%. So 200%. Right? Because 2x would be 100%. So another 100% on top of that. All right. So like you see where this is going. So 1.25, that's the growth factor. Right? And it's growing because it's bigger than 1, right? 1.25. Now the question is, how much bigger than 1 is it? Well, it's 0.25 bigger. So 25%. All right, and last 0.52. This is definitely decay. And it's decay because it's less than 1. Right, look. Look, bigger than 1. Decay, less than 1. I guess I could have used math symbols, but I want you to know, less than 1. All right. And how much less than 1? That's the question. 0.48. So 48%. Okay, so the thing here is if it's bigger than 1, it's growth. If it's less than 1, it's decay. Now, bigger than 1 is the obvious, right? How much is it bigger than 1? It's the decay that you got to think. You got to think. Almost done. Okay. All right. Uninhibited growth and decay. You may use a calculator. All right. The number of hits a new search engine website receives each month can be modeled by this right here. Uninhibited growth, where K is 0.2446. Okay. So here it's the same idea, right? You have some starting number, E to the KT, right? Notice how similar this is. I mean, it's basically the same thing. It's just that they're using different letters because it's a different kind of like scenario, I guess you could say. It's uninhibited growth, whatever. All right, you still have some starting amount, E to the rate times time. The only thing in here is that time, T, doesn't necessarily have to be in years the way it is in normal exponential growth, right? T is whatever they say. So notice in A, it's saying 2 months. So T is definitely months. So a website receives 4800 E, and it's growing because K is positive. 0.2446 times 2 because it's 2 months to the calculator. All right, it receives this many hits. 7,828. Okay. How long will it take to double the number of hits per month? Okay, so it started with 4,800. We want to double it. So whatever 48 times 2 is. So 96. So there are a couple different ways to think about this. So what I'm doing is I'm taking 4,800, right? The thing we're starting with, and then 0.2446 T, because we don't know what T is. And I want it to double. So 9,600 would be double. All right, so because we're solving for T, when we divide both sides by 4,800, right? Because I'm trying to isolate this E business off to the right. So this is going to be 2. So technically, we could have forgot about the initial amount, right? We don't really care about the initial amount anymore. If you take the E to the rate times T instead equal to 2, right? This is how you figure out how long it takes something to double. For instance, if they said how much would the half-life be, half of something, then you would do 1/2. Like you forget about the initial amount, right? Because no matter what amount you put here, so say if I would have started with 1, and I want to see how long does it take to double. Okay, well 2. Then when you divide it over, 2 divided by 1. Say if I started with 100, and I want to say how long does it take to double. Well, double would be 200. Then 200 divided by 100 would still be 2. So no matter what numbers you use, you're always going to have 2. You know what I'm saying? So you're always going to have 2. All right. So now we can either graph the right side and graph the left side and see where they intersect, or just start hand jamming numbers. So about 3 months. Right. So that number, whatever number we get, you gotta look and see what was the time actually. So 3 months. Okay. Number 2. We're almost done. All right. Iridium is used to treat some types of cancer. It decays following the law of uninhibited decay. So decay, K needs to be negative, which it is. So what is the half-life? There's that word half-life. So I'm going to set, so 1/2, which is really 0.5. E to the negative 0.00938 T. So notice there's no initial amount because I'm trying to figure out the half-life. Now, say if you don't like doing that, I don't know why you wouldn't, but you just pick a number. Like 1. I don't know. One's a bad example. So like 2. You start with 2 and you want to cut it in half. So 1. So you would have 2 here and 1 here. So when you divide the 2 over, you're going to get 1 divided by 2. And 1 divided by 2 is 0.5. And it doesn't matter what number you use, right? If you started with 20 and you want to know how much would it take to get to 10, right? Because that's half of 20. You would divide the 20 over. 10 divided by 20 reduces to 1/2. So what I'm saying is you don't need to have an initial amount. If we're doing half-life, we can just do 0.5. So let's start figuring that out. About 73 days. That was just brute force. Once we hit logarithms, um, there's a way easier way of figuring this out. All right. So if your hospital has 36 micrograms in the pharmacy today, how much will be active 1 week from now? Okay, so 36 is the initial amount. So 36 e to the negative 0.00938 times 1 week. So remember, T was days. T is days. So 7 days. There's 7 days in a week. So 36 e negative 0.00938 times 7. So how much? 33.712. That's how much will be active. All right. If you predict that 40 days from now, you will need 18 milligrams, do you have enough in storage or will you need to order more? Okay, so it's a continuation from B. So they're saying that we have 36 in the pharmacy today, 36 micrograms. All right, if you predict that 40 days from now, you will need 18. All right, so let's do 40. All right, so I'm starting with 36, and 40 days from now, we'll have the calculator tells me 24, but we need 18. So we have enough, right? We have enough. If I have 36 right now, and 40 days from now, I need 18. Well, 40 days from now, I'll have 24, and 24 is 18. So yes, we have enough. We good. All right. Number 3. Archaeologists exploring an ancient African site find that pieces of wood tools contain 16% of the original carbon 14. All right, there's the decay rate. T is in years. How old are the tools? Okay, so what this is saying is 16% is equal to is the initial amount 100? That's an excellent question. Dang, I feel like it's 100. Okay. E 24 T. I don't remember if it's 100 or 1,000 or if there's even a number. I think it's 100. I think it's 100. Let's see what happens. So no, I don't think we put anything, to be quite honest. I was right. It is 100. Okay. So I think this one is definitely a graphing one because you're going to be here for a minute trying to trial and error the T's. All right. So All right. So when I graph 100e to that, and then I graph another line, 16, and I see where they intersect, it tells me that t is going to be equal I lost it. All right, so 1477.8.88. All right, so how old are the tools when t is in years? So 14,000 years. 14,778. Okay. That one's really wish I could have showed you what was on the calculator. All right, another sore throat. All right, so you caught the cooties and currently have 2,220 bacteria in your nose and throat. Assume the growth of this bacteria follows the uninhibited growth. So here's K, and T is hours. How long will it take for the bacteria colony to double in size? So again, we got E 0.1155 T, and we want to know how long will it take to double, right, to equal 2. So I wonder, I'm going to change the graph. So e to the 0.1155, no coefficient. All right, there's my graph. Two, and I see where do they intersect. So 6 hours. Caught the virus at 11 a.m. on Monday. How many bacteria in your nose and throat at 2:30 on Wednesday? All right, so 11 a.m. So think about it. 11 a.m. on Monday to 11 a.m. on Tuesday is 12 hours. No, 24 hours. Right, one whole day. All right, 11 a.m. on Tuesday to 11 a.m. on Wednesday is another 24 hours. So 11 a.m. on Wednesday. 11, 12, 1, 2. So 3 hours. But 30-minute window. So 0.5 of an hour. Right, because 30 minutes is 0.5, right? That's half an hour. So you add these up. This is going to be all right, 51.5. So 51.5. That's the hours that we're going that's our T. So we're going to plug it into our model. E. Well, don't forget that we're starting with 2,220. We're starting with 2,220. So 2,220 e to the, was it 0.1155 times 51.5. So eight five 0442. All right, if you start taking antibiotics at 9:30 a.m. Thursday, how many bacteria are there when the medicine starts to take effect 2 hours later? Okay, so 2:30 on Wednesday was 51.5, right? That's what it was. That's what we just figured out. 2:30 on Wednesday. All right, 9:30 Thursday. So let's think about that for just a moment. So 2:30 Wednesday afternoon. So 2:30 to 2:30 at night. Right? That'd be Thursday morning, 2:30 a.m. So that's 12 hours has gone by. So 2:30, then 3:30, 4:30, 5:30, 6:30, 7:30, 8:30, 9:30. So 7 more hours on top of that. So 51.5 plus 19 hours. So 70.5. So 70.5. That's at 9:30. But you took the antibiotics and it doesn't take effect for 2 more hours. So really, it's 72.5. Okay, that's our T. So hopefully you can follow me on the logic on that. All right, so 72 hours. So I'm just going to plug in 72 for my T. So up, enter. 72.5. All right, so we got a ton of yuck. So 9616707. All right, the medicine creates a decline in bacteria that follows the law of uninhibited decay, with that K and T is hours. How many bacteria are left 3 days after you start the medicine? Okay, so then we started the medicine. So let's think about what that's asking. How many bacteria are left 3 days after you start the medicine? All right, so when I started the medicine, or when the medicine starts to take effect, that's how you want to interpret this. I mean, words mean things. It says after you start the medicine. Okay, well I started it, and just because it took 2 hours, so what does that mean? Do I need to calculate at 70.5, or do we just use this number? You know, I'm lazy. Let's just use this number. Let's just say that 3 days after this. So I took the medicine at 9:30, 10:30, 11:30. That's when it started to take effect. 11:30, and then how many bacteria are left 3 days after you start the medicine? So 3 days. What is that? 72 hours. So 72 hours later. So 3 days is 72 hours, right? 24 times 3, 24, 48, 72. So if I use the number that we started with, so 9616707, E negative 0.01 444 times 72. Okay, let's go. We're getting well. So this is going to be 3400157. So we still got about 3 million. It's better than 9 million. All right. Okay, part 4 I already did. All right, here we are at the last one. All right. So here's our chart. Assume that the change is in the bug colony can be modeled using an exponential function. Find the regression. All right. Fast forward to this part. All right, so new document. No, I don't want to save. Listen spreadsheets. X and Y at the top, and then just start plugging. So look, number of days is my X, number of bugs is the Y's. Time is usually on the X axis, the horizontal axis. So after I plug it in, Control Doc 5 makes the points. So Y on the vertical, X on the horizontal. All right, it grows exponentially. And then menu, analyze, regression, exponential, number 8. Okay, so find the regression for the data. All right, I did. What does each number? Okay, so the equation, I guess, is what it's asking. It's 25.888. I mean, do you have to write all these out? No, not necessarily, but you know, we want to be precise. Says the guy that makes the most mistakes. All right, so here's the equation. So what do each of these numbers represent? Okay, so this is some starting amount or some initial amount, and then this is the growth factor. So the initial amount or starting amount. And that makes sense, right? Because if you look here at day number 0, we had 26 bugs, and 25.888 is basically 26. And then we have the growth factor, right? How much is it increasing? It's increasing 24%. Why is it 24%? Because that's how much it's above 1, right? It's increasing per day, 25% per day. Okay. Since the biologist didn't take account on day 4, so up here in our little chart, we have days 1, 2, 3, but no 4, right? Where's day 4 at? So we want to use your equation to interpolate the number of bugs on day 4. So this means X equals 4. So we take our model and we plug in 4 for X. Right, and it's just a model. So about 63.0 blah blah blah. 63. All right. We're going to extrapolate for day 10. Right, because our chart only goes up to 7. So we're looking for day 10. Up, enter. Change 4 to 10. 239. Okay, what do you think the difference is in the words interpolate and extrapolate? All right, so check it out. Here we're given 0 to 7, right? 0 to 7. All right. Anything in between 0 and 7, i.e., we had 4, we can figure out anything in between the given range, right? 0 to 7, and inside of the given interval. So that's interpolate. Anything inside, interpolate. Extrapolate is going to be anything that's outside of the given interval. So 0 to 7, any number that's not in between 0 and 7 exclusively will be extrapolating. Anything that's inside, in between 0 and 7 is interpolate because it's in between 0 and 7. You feel me? All right. So that's what it means. Right? Interpolate would be inside the range. Not range like in Y, but like the given interval. Inside interval, interpolate. And extrapolate is outside the interval. And now, like, again, you say, well, what interval? Like the highest amount that they gave us, right? 7. Anything bigger than 7, I can extrapolate. Anything less than 7, but bigger than 0, I can interpolate. That's what it means. All right. What is the y-intercept? Okay, the y-intercept when x is 0. When x is 0, we're going to get 26, right? Because that's how much we started with. When x is 0, that's the y-intercept. What is the meaning of the y-intercept in relation to this particular situation? It means on day 0, what did we start with? That's what it means. All right, how many bugs were present 2 days before they even started this? Okay, so now think. Time can't be negative, obviously, but mathematically it can, right? Like, so 2 days before would be -2 because this goes by days. So if I put x equals -2, there would be 16. Okay. Is that it? Hope that's it. All right. Good luck. Peace.